Good morning, class. Hope you had a good weekend. And see, I got a few announcements for you. So I finished grading your exams from last Monday and posted your exam scores on Sakai. So they're posted on Sakai, but they're not figured into your course grade yet on WebAssign. I just got to move the grades from Sakai to WebAssign. But please go review your exam score, read the comments. It's a little challenging to give you feedback in the most effective way because normally I would just mark up your exam and give you the hard copy back for review. But in the case of submitting stuff electronically, I'm posting the exam solutions on Sakai, so you can go there and you can view the exams, my solutions, my worked out solutions. And it is necessary that you review this exam and strive to learn from your mistakes or strengthen the parts that you had difficulty with, because final exam will be cumulative. Okay, so that's posted. We talked a little about it on Friday during our Zoom session, and I took some questions. Review your score, email me if you have any questions or concerns. Okay, so that's posted. Homework on momentum is posted. Please be working on that. Today we're going to do a derivation of conservation of momentum. So we talked a lot about momentum and experimented with a simulation last week. So today we're going to be more quantitative, and I'm going to start by proposing that this quantity momentum is conserved during a collision, an interaction between two objects, and then we'll go about seeing if we can prove that that's the case. All right, so that's what's on tap today, and hopefully before we're done here, we'll be able to actually go through one of the problems that are assigned, and we can discuss how it's done. All right, so let's go on over to remote desktop, and I don't know why, but my computer is running hot today. So hopefully, I don't know, something's using a lot of resources here. I don't think anything's open. All right, so let's get started here. Momentum is conserved. I wonder if it's I think it's my OneDrive going crazy. Hold on a second. Control Alt Delete. Running hot here. I'm gonna kill OneDrive. Bye-bye. All right, we'll see if that helps. All right, momentum is conserved. So let's start out with definition of momentum. So we talked a lot about this, and in words we said, an object has momentum if it has mass and velocity. So here's an object A. It has mass A and it has velocity A. And momentum which we'll abbreviate capital P, is a vector quantity equal to its mass times its velocity. Okay, so momentum is this quantity, the product of mass and velocity. Because it contains velocity, it's a vector quantity as well. So it's a vector, it has magnitude, and it has direction. Okay, and so I'm going to make let's consider a scenario like this. We have object A moving in this direction, yeah, I know, why is that still up there? Object B moving in this direction, and we have velocity A and velocity B. So we got these things on a collision course. And I'm going to make the preposition here that if you calculated the total momentum of the system, what would that be? It would be the momentum of object A plus the momentum of object B, and that equals some total. And I'm going to make I'm going to propose to you that this value is constant even if they collide. So sometime in the future, A and B collide, they interact with one another. And there's a lot going on during this collision. And then after they collide, A is doing something different, and B is doing something different. So we'll call that VA. I could call these VA initials and finals, but I'm going to call this VA prime. And so the prime means after they collided. Okay, so this is before, and then this is after they collided. Okay, and I'm going to propose to you that the total momentum after the collision, call that P total prime, which is the sum of the momentum of object 1 after PA prime plus the momentum of object B after PB prime. I'm going to propose to you that those two quantities are equal to one another. So I'm proposing that the total momentum before is equal to total momentum after. So this is before, and this is after. All right, so we did a lot of simulations last week that showed that, well, at least in the simulation world, this was true. And it meant that the momentum could move from one object to another, but the total momentum was the same. Okay, so let's go about seeing if we can prove that this is the case. And so one caveat here, and that's that let's refer to this as an isolated system. And so what does that mean exactly? It means that there's no external influences or external forces. So the only forces that are involved in this collision are the force of A pushing on B and B pushing on A during this collision. Okay, there's nothing external, so there's no friction, there's no external forces pushing or pulling, like gravity. This is an isolated system. And so in the real world, are systems isolated? Well, sometimes more so than others, but most collisions happen quickly, and for, you know, for short duration interactions like that, we can, you know, the forces of interactions are much greater than the external forces on the system. So we can usually ignore external influences. All right. So let's focus in on the collision. Make this. All right. So this is my proposition. Let's go over here, and let me use two different colors. All right. So here is object A, and here is object B, and they collide. And so during this collision, there's a force that object A exerts on object B, and there's a force that object B exerts on object A. Okay? There's a force. Interactions involve forces. So what do you know about the strength of those forces during that interaction? So tell me in the comments here. Tell me in the chat window, what do you know about those forces of interaction? Do you know? Such a dreary day today. And yesterday. It was not the greatest weekend. But I got your exams graded. Come on, guys. Be alive. Who's alive out there? What do you know about these forces? You know, force A exerts on B, and the reaction is force B exerting on A. You have forces of interaction. Hi, Holly. Me? They're equal. Thank you, Holly. So they're equal. That's Newton's third law. You have forces occur in action-reaction force pairs. So if you have two objects that are colliding with one another, this is true. You know, I mean, in the exam this last week, it was a baseball bat and a baseball. So if the ball 1 exerts a force of 100 newtons on ball 2, then ball 2 exerts 100 newtons back. All right, so Newton's third law says these forces are equal in magnitude but opposite in direction. All right, so we can represent the direction with a positive or a negative sign. All right, so let's simplify things to one dimension here. We can represent the direction with a positive or a negative sign, and the magnitudes are equal to one another. So that sets up an equation. All right. So this sets up an equation like this. FAB equals negative FBA. Okay, they're equal to one another. And so now we'll talk about something different here. All right, so interactions have a force, and then interactions also have a duration. And well, how do you think, so the duration, I mean time. You know, so there's this collision between two objects. And if you were timing how long that collision was from the perspective of billiard ball A, you know, there's a little guy with a stopwatch sitting on top of that billiard ball timing how long that interaction was. And then there's another guy timing how long the interaction was on billiard ball B. How would the times compare? You know, so if you're looking at an interaction, a collision between two objects, you're looking at it from the perspective of object A or object B, how would the duration, the amount of time for that interaction compare depending on the perspective? Would it be the same? Would it be different? What do you say? would they be the same or would they be different? Time, duration. You know, think of bat hitting ball, ball hitting bat, car hitting truck, truck hitting car. Presumably the same, right? Yeah, thank you, William. So the time of interaction is the same, all right? So that allows us to extend, so there's, let's call it a dt, a short amount of time, infinitesimally small amount of time. So there's a small amount of time, and, whoops. Let's multiply this by that small amount of time because it's the same from both, the time of interaction is the same. Let me just switch over to all black here, make it easier. So we have this quantity, force times an interval of time. Oops, forgot the negative sign. Equals FAB dt equals negative FBA dt. So what we've defined here is, this is called impulse. Impulse. So impulse is a physics quantity, which is the product of a force and a time. And but right now, you know, so this is like, you know, an infinitesimally small impulse because I'm writing it as a dt. So you can imagine integrating both sides over the entire duration of the collision and getting some total amount of impulse for the entire collision. And that might be important because, you know, with collisions, the force of interaction may change. At any moment in time, the amount of force between the two objects, A on B, B on A, is the same magnitude, opposite directions. But you can easily imagine a situation where the magnitude of that force changes over time. So, you know, this could be a result of deformation. You know, balls bounce, they deform, they squish, and the force of impact can change over time. But this quantity, this impulse, you could think of it as in a different way. And so let's do that. We know that force from Newton's second law is mass times acceleration. So let's put that into this expression and see how it changes things. All right. So from Newton's second law, we know force equals mass times acceleration. And let's use the derivative definition of acceleration. Acceleration is a dv over dt, a change in velocity with respect to time. So let's put that into this expression and see how that changes things. So FAB, the force of A on B, is going to equal the mass of B times this change in velocity with respect to time. So this would become mb dv b divided by dt times dt equals negative ma dva dt times dt. So the forces become masses times accelerations, or masses times changes in velocity with respect to time. And now we have this like sort of change of perspective because the dt's all cancel, and then what we're left with is something that looks like this. Let me write that again. And so then you can imagine integrating these expressions over the entire collision. And when you do that, you know, you get the total, so these are written as terms of an infinitesimally small change in velocity. If you integrate over the whole collision, you get the total change in velocity. So let's write that as a delta v. So this would become mb delta v b equals negative ma delta v a. Okay, so we've done this like sort of change in variables, but we're still dealing with this quantity called impulse. Okay, so we could say that, impulse equals two things. It's a force times the duration in time, or it's equal to a mass times a change in velocity, which is really, mass times velocity is what? It's a change in momentum. So impulse can be thought of as a force times the duration in time, or a change in momentum. That's what we found here. So what we discover here is that Newton's third law, and then putting in Newton's second law, the connection between force and acceleration. But if we do this and study an interaction between two objects, what we find is that the impulse experienced by one of those objects is equal to the negative impulse of the other object. Okay, so to say that in other words, let's think in terms of change in momentum. The change in momentum of object A is equal to the negative change in momentum of object B. Okay, so what do you get if you add those two changes together? You have a delta P sub A and a delta P sub B, and if you add them together, what do you get? Alright, so to summarize over here, I'm saying, this result is that the change in momentum of object A is equal to the negative change in momentum of object B. Alright, so let's come back over here and let's think about, what's another way that you can think about this proposition that I gave you? The total before is the total after. Another way of saying that is the change in momentum equals 0. In other words, momentum is conserved. Okay? Another way of saying this, that the total before equals the total after, is that delta P is 0. Okay? Well, what is delta P total? It's the total momentum of the system. It's equal to the change in momentum of A plus the change in momentum of B. And we just discovered that those two quantities are equal in magnitude but opposite in direction. So it must be equal to 0. Okay? You got to be equal to 0. So that's what it means to say momentum is conserved. So when you have an interaction, and this follows directly from Newton's laws, Newton's third law and Newton's second law. If you have an interaction, the only thing, you're just focusing on that interaction, external influences are ignored or not important. Newton's third law says the force of that interaction is the same. The action and the reaction force are the same magnitude but opposite in direction. And when you follow that through by saying, well, the duration of the interaction is the same, and then think about how, the connection between forces, accelerations, and velocities, you find momentum popping up in this expression, this equality. And when you do that, you find that this new thing that we were calling impulse, it's sort of like, the Newton's third law applied to momentum is for every impulse, there's an equal and opposite impulse. Instead of saying for every force, there's an equal and oppositely directed force. For every impulse, there's an equal in magnitude but opposite in direction impulse. And impulse is a vector quantity too. It's a change in momentum. So it has a direction associated with it. All right, and then the consequence of that is that the total momentum of the system that you're considering is conserved. That if object A loses momentum, has a negative impulse, object B will gain momentum. It'll have a positive impulse, but the sum of those two impulses is 0. All right, so that's conservation of momentum in its entirety. And we could add a second dimension to this situation, and we could say, well, how is we're dealing with vector quantities, so how is momentum conserved when you have two dimensions? Well, you could break it into two parts, and you have an x direction, a y direction, and momentum is conserved in both of those directions simultaneously. All right, so then there's another piece here that allows us to solve problems. The other thing that we saw last week with the simulation was that momentum was conserved, the total momentum of the system was conserved, but kinetic energy not so much. Kinetic energy was only conserved when you had a completely elastic collision. If the collision was inelastic or completely inelastic, like two things come together and stick, kinetic energy was not conserved. So that's another tool that we can use. We can use conservation of momentum to problem solve collisions, regardless of the nature of that collision. But if the collision is also elastic, we can also use conservation of mechanical energy, conservation of kinetic energy to study those interactions. All right, but only if they're elastic collisions. All right, let's do a problem. All right, guys. So stay awake, stay lively. Let's take a look at one of the homework problems. There's a problem in the textbook which involves two rail cars. There's a problem in the homework assignment, it's in the textbook too, of two rail cars that collide. They're traveling in opposite directions. They collide and stick together. Okay. And the symbols that are used on WebAssign and in your textbook are a little different than my preference. My preference is to use the prime. I have these quantities before and after. I like to use little primes to denote after collisions. Before is no prime, after has a little, little prime symbol. But the textbook doesn't. So let's do one problem using the notation that the textbook likes. The textbook likes subscripts I or F for initial and final. So let's do it that way here. All right, and it doesn't like A's and B's, it likes 1's and 2's. So the mass of railcar 1 is given to us in this problem. And for me, it was 15,000 kilograms, or 1.54 times 10 to the 5th kilograms. And the mass of train car 2 was somewhat lighter. Okay, and before they collide, train car 1, so let's call that V1I for initial, is 0.3 meters per second I hat, which means positive x direction. All right, so that's the this is a one-dimensional problem, and that direction is the positive x direction. All right, and V2 initial is negative, it's moving in the opposite direction, 0.12 meters per second I hat. Okay, so we got two train cars moving in opposite direction. This is before. And then after they collide, they stick together, they get coupled together. So they have sticking together now, and they're moving with some final velocity, and I think it's going to be to the right. I'm not entirely sure, but let's assume it's to the right. And if we get an answer that's positive, that tells us our assumption here is correct. If we get an answer that's negative, it tells us our initial assumption about the combined cars moving to the right was incorrect, and we just got to flip the direction. And so let's set up our condition for momentum being conserved. We're assuming external influences like friction between the track and the wheels and all that are negligible, so we can ignore it. And what we'll have is we can set up an expression that says the total momentum before, here I'll use the I subscript for initial, like the textbook likes, is the total equal to the total momentum after the collision. So use the F. So now we just expand these out. Well, there's two bodies here. The total momentum before would be the momentum of 1 initial plus the momentum of train car 2 initial, and that equals the momentum of train car 1 final plus the momentum of train car 2 final. And now we know momentum is mass times velocity. So this is m1 v1 initial, and let's do minus m2 v2 initial. And I have a minus sign because I'm taking into account the direction. So I've already taken into account the minus sign in the velocity. Okay? If I had a plus sign there, I hadn't done that yet, but I already did. So from that point forward, I'm just worried about the magnitude of velocities. And that equals the momentum of train car 1 after P1F plus the momentum of train car 2 after. Oh, whoops, I'm writing these out. M1 V1 final plus M2 V2 final. And what do we see over here? Well, if you have, this is a situation of a completely inelastic collision. Okay, it's a completely inelastic collision. How do we know? Because they stick together. They get coupled together after the collision. All right, and that means if they stick together, V1 final equals V2 final. It's some common velocity. They have the same velocity afterwards if they stick together. So in this expression down here, the V1F and the V2F are the same. So we can factor that out. And so when you have a collision like this, a completely inelastic collision, after the collision, it's like you only have one body. There's no longer two separate things. There's just one body with one velocity and a mass equal to the combined mass of the two things that combined, M1 plus M2. Okay. So we could solve for V final now. V final is going to equal M1 V1 initial minus M2 V2 initial divided by the total mass. All right, so I just dropped the vector notation because it's one-dimensional, and we've already taken into account the fact that train car 2 is traveling to the left before the collision. All right, so when I plug all these values in, what I get is an answer of about positive 0.131 meters per second. Okay, so that means V final is equal to 0.131 meters per second I hat. It's traveling in the positive x direction. Right, there's my answer here. All right, and that is correct. That is correct for this problem. checked it with the homework, and that's the correct answer. All right, so for all these problems that involve conservation of momentum, it always starts, just like in the last unit with energy, every problem starts with the work energy theorem. Change in kinetic plus change in potential equals work done by non-conservative forces. So if there's no non-conservative forces, the change in kinetic plus the change in potential is zero, and we called that conservation of mechanical energy. All right. So in the case of momentum, the problem solving starts with this definition of momentum being conserved. The total momentum before the collision equals the total momentum after the collision. So the notable differences here are now you're thinking about systems. All right, you're not thinking about individual objects, you're thinking about systems, and those systems have at least two bodies that interact, two objects that interact, collisions. You could also have one body that explodes into two or more smaller bodies, and that's sort of like, an explosion is playing a completely inelastic collision in reverse. If you had a movie of two things colliding and sticking together and played it in reverse, it would be an explosion. All right, but the principle of momentum conservation holds. Okay. So what about, and you set up an equation, total before equals total after, and there's some quantity you don't know in that expression once you write it all out and you algebraically solve. So let's take a little bit deeper look at this special case. All right, so everything we've done so far is general to all collisions when you can ignore external influences. But let's look at this special case where not only the special case is elastic collisions, completely elastic collisions. Okay, and in cases like this, not only is momentum conserved, but kinetic energy is conserved as well. The kinetic energy of the system before the collision equals the kinetic energy after. Okay. So, this is always the case, all right, when you're dealing with collisions. But now let's look at a special case. And that special case is elastic collision. Completely I can't spell. Completely elastic collision. Okay, so this will be a situation where you have two objects that collide, and let's say they're moving in opposite directions initially. Don't necessarily have to be. Maybe A just catches up to B, and they collide. And then after they collide, they're moving in another direction. They're moving with some other velocity. So let's go back to my prime notation. Whoops. Well, if I'm going to do it, I better do it right. So we have VA and VB, and then we have VA prime and VB prime. Okay, and there's masses associated with A and B. Okay, so the first thing we saw, if momentum is conserved, which it is, you have MA VA prime plus, MA VA plus MB VB equals ma va prime plus mb vb prime. Okay, so that's a statement of momentum being conserved. The total momentum before equals the total after. But if it's an elastic collision, we also have that the kinetic energy, and kinetic energy is a scalar quantity, so it's not velocity here, it's speed squared. But before the collision, the kinetic energy of mass A plus the kinetic energy of mass B equals the kinetic energy, this is a little awkward to write, it's VA prime squared, because it's the speed after the collision, plus VB prime squared. Alright, so if kinetic energy is conserved in the case of elastic equation, we can say that the total kinetic energy before the collision, 1/2 ma va squared plus 1/2 mb vb squared, equals the total kinetic energy after the collision, 1/2 ma va prime squared plus 1/2 mb vb prime squared. And so now we have two equations that we can use to solve problems. And if you have two equations, that means you can attack problems that have two unknowns. Two equations, you need systems of equations, two unknowns to solve them. So an example of this would be, let's say you have a collision and you know the pre-collision velocities and masses, but you don't know anything about what happens after the collision, how fast they're going in what direction. If it's an elastic collision, you can solve that problem by using, because then there's two unknowns, VA prime and VB prime, the velocity of mass A after the collision and the velocity of mass B after the collision. If they're both unknown, but it's an elastic collision, you can solve that problem. But you know, this way of writing out this equation is, what I'm saying is this equation is not very user friendly. You know, you have square quantity. You know, one thing you could do is you see that everything has a half in it, so the halves you can multiply by 2 and all those halves go away, but you still have squared quantities. One thing you can do is, if you have two equations, you can combine them to get a simpler form of one of them. So we can combine these two equations, and I'll skip the algebra here. You can look at your textbook if you want to see how this is done, but when you combine these two equations, a lot of simplification occurs, and you end with an expression that looks like this: VA minus VB equals VB minus VA. Okay? And so when you attack problems like this, you can use that expression and this expression as two equations, the two unknowns, and then completely ignore this big long thing that has squared terms in it. Okay, so I'm say that one more time. Algebraically, if you combine these two expressions, the one for momentum being conserved and the one for kinetic energy being conserved, that combined expression simplifies to this third expression that I just wrote. And so then you can use that third equation combined with the condition of momentum being conserved for problem solving. And you never actually have to write out this conservation of kinetic energy equation. Okay. Again, this only applies if the collision is elastic. All right. If it's an inelastic or completely inelastic collision, you can't use conservation of kinetic energy because it's not conserved. All right. So what is this thing? What does that look like? Well, we have VA minus VB. Basically, what we have is VA minus VB equals VB minus VA. So we have the same. Oh shoot! I forgot something. I forgot the primes. sorry. Before it didn't make any sense. So the difference in velocities before the collision, VA minus VB, equals the negative of that difference after the collision. The order is switched. Okay, negative those the velocity of B and A after the collision. So what is it? What is VA minus VB? It's a relative velocity, or as I wrote it here, a relative speed. VA minus VB is how fast object A is traveling relative to object B. So if you know, two trains on a collision course, and A is going this way at 10 meters per second, and B is going this way at 10 meters per second, then the velocity of A relative to B is not 10, it's 20 meters per second, because that's the rate at which they're converging. And if they collide elastically and then go the opposite direction, now instead of converging at 20 meters per second, they're diverging. They're getting further apart at 20 meters per second. Okay, so that's why the order of these terms is switched. VA minus VB equals VB prime minus VA prime. Okay, the relative velocity has relative speed is the same, but the relative velocity is switched in direction. All right, that's what I'm saying here. So let's end today. Well, let's end right there. All right, I was going to pull up the simulation and look and show you that this holds in the simulation of an elastic collision, but we'll do that again some other time. All right, that's it for today. Any questions? Let me pause here. Let me look at the chat window. You guys are so quiet, and there's only 14 of you in here today. Oh, come on, guys. I know, well, I can't tell you to come on, guys. You're all here. You know, if you watch this later, a recording, it's better than nothing. But if you're watching this after class, try to tune in during the class time. All right, guys. I will see you guys tomorrow afternoon. All right, tomorrow afternoon we'll talk about the lab this week. And then Wednesday we'll pick up and do a few more example problems. So there is a problem in the homework which is really challenging. It's a two-dimensional collision. That is going to be the topic of my next video tutorial. Okay, so look for that coming out sometime this week. All right, see you guys tomorrow.